This is Mr. Gillum, and today we're going to be looking at page 168 in your instruction book, talking about properties of operations. Before I talk about this example, we talked about three different properties yesterday in the notes, the commutative property, the associative property, and the distributive property. And I just want to really make sure that we're clear about how those things, I might be using the words commutative, associative, or distributive in this example video, and I want to make sure that you know what they mean. So the commutative property, and that's not commutative, it's commutative, has to do with the order. Okay, and we specifically talked about yesterday the commutative property of addition, meaning you can add in any order. Okay, so commutative and order have to do with one another. So when you're switching the order of the expression, you're switching term values in different orders, that's called the commutative property of addition. Later, we're going to learn about the commutative property of multiplication, which also says, okay, you can also, just like addition, you can switch around the order of multiplication and still have the same outcome. Okay. The associative property, that has to do with parentheses, so grouping symbols. That just says that if you have of addition is what we talked about, but it works for multiplication as well. Basically says if you have a long list of addition in your expression and part of them are being grouped, you can group them according to how you want to use your strategy. So one of the strategies we talked about yesterday was you can group by finding numbers that add to 10. Okay, and on your Math League stuff, that's going to be, I'm sure you'll see that on there, where if you are a good grouper or you know that strategy, then I know that you'll answer those questions more accurately and quicker than your classmates. So associative property has to do with grouping or parentheses. Okay, you think we know the distributive property because we talked about it quite a bit. The distributive property says two things. It says you can take a number and you can multiply it by each part inside, or you can use the greatest common factor of two numbers, and you can take the greatest common factor outside. So this number will be the greatest common factor. So the distributive property works front ways and back ways. So those are the three properties that we learned yesterday. And again, this is kind of vocabulary based, so it's important to remember what each of those things does. It says Jamie has 4 bags of apples and Ashley has 3 bags of apples. Each bag has the same number of apples in it. Okay. Write an expression for the total number of apples, then simplify it to create an equivalent expression. So this could be confusing because Jamie's bags are kind of different than Ashley's bags, I guess. So you might think that Jamie's bags of apples have a different number of apples than Ashley's bags, but it doesn't really say that. It just says that each bag has the same number in it. So all 4 of Jamie's bags and all 3 of Ashley's bags, every single bag in the entire word problem has the same number of apples. Jamie just has a different number of bags than Ashley does. So if we pictured this and you can see they drew out actually 4 bags and there's apples inside each one, we just don't know how many apples, but we do know that each bag has the same number of apples. So although the number inside is unknown, we do know that it's all the same in each one. So you can see that we have 7 bags here, Jamie's bags and Ashley's bags, and you can see also that we don't know how many's in, but we didn't have to use a different variable for each bag because we know that the number inside is actually the same for each one. So we have 7 X's here, 1, 2, 3, 4, 5, 6, 7. And if we have 7 x's, instead of counting 1, 2, 3, 4, 5, 6, 7, we could really just take 7 times x. If this was 1 apple in each bag, or 2 apples in each bag, 2, 4, 6, 8, 10, 12, 14, we could just instead do 7 times 2, which would also be 14. So I want you to just think about that. And that's why we can say x plus x plus x plus x plus x plus x plus x really is the same as 7 times x, or 7 x's. We could also model it, same problem. So you can see it's very similar. They just didn't draw bags. They actually just drew like rectangles to represent bags. So it's called modeling. It's just basically another form of algebra where one thing represents another. In this case, a rectangle represents a bag. It says model the bag with math tiles. So we have 4 bags of apples for Jamie and 3 for Ashley. Again, we have 7 bags full of the same number of apples, so we really have 7 x's. So it says in both picture and model it on the previous page, what does x represent? Well, x actually represents the number of, it's written here for us in this one, the number of apples, the unknown number of apples. Although it's unknown, we can use X for every single bag because it's the same unknown number each time, and that's indicated by the same number of apples in it. I mean, we know that each bag has the same number. So that's to write an expression for Jamie's total number of apples. So 2 expressions would be appropriate here because there's 7 bags. You could write, like I said, X plus X plus X plus X plus X plus X plus X, which would be fine. That would be true, but really what we have is instead of adding X, whatever that number is, up 7 times, like if I add 3 up 7 times, really what I'm doing is I'm taking 3 times 7 or 7 times 3. So Jamie's number of apples would be 4x. He had 4 bags, and the number of apples inside each one of them is unknown, so 4x. And for Ashley's total, she had 3 bags, so we could call her 3x, but we could also say x plus x plus x. 3x is really more appropriate. We call that simplifying the expression. It says write an expression for the combined total of Jamie's and Ashley's apples. Again, instead of writing x plus x plus blah, 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 on and on and on, it's a much more efficient way to write. Would be 4x plus 3x. If we're talking about Jamie's and Ashley's apples, you could even write 7x if you would like. Okay. I guess they will kind of want you to write 4x plus 3x just so that you can keep Jamie's bags and Ashley's bags separate, although we know that there's the same number of apples inside, so 7x would be appropriate as well. Says when 2 or more terms in a variable expression have the same variable factors, they are called like terms. You can use the distributive property to simplify an expression with like terms. So we have actually talked a little bit about like terms, and I think when we talked it was on the board, but if they have the same exact variable part, including the exponent, everything must be exactly the same, then you can combine them. The operation in front of the term represents the positivity or negativity of that term. So let's take a look. But there's some examples here. It says, what's the common factor for each term in your expression from problem 3? Now, this can be very tricky. If I have an expression 4x plus 3x, okay, and they kept them separate in this case. I'll write it over here. We started with 4x plus 3x. We practiced in the past finding the factors of 4 and the factors of 3 and finding the greatest common factor. In this case, it's just 1. So in this case, there are no number factors that are the same that are going to change what would be inside the parentheses. Because if I took a 1 outside the parentheses with the distributive property, I would still have 4x plus 3x. And I already know I have 4x plus 3x. So it's not actually talking about the factors as far as numbers go in this case. It's actually talking about the variable part, because keep in mind a variable really does represent a number. So in this case, the factors that they have in common is actually the variable factor, x. X is the factor they have in common. Instead of 1, we're going to use the letter x. So if I use the distributive property, what it's going to look like is x times 4 plus 3. I'm actually going to take, instead of a number outside the parentheses, I'm going to take a letter. X times 4 would be 4x, and x times 3 would be 3x. And so using the distributive property, I can see, oh, look, now I can combine 4 and 3 together. So really I have x times 7, but we would write that as 7x. And that's why we can combine like terms. So 4x is in here, 3x is there, makes 7x's all together. Really, the reason we can do that has to do with the distributive property. What does the simplified expression mean? Well, that represents the total number of, it will eventually represent the total number of apples, but right now it represents there are 7 bags of the same number of apples in each bag. Explain how to simplify an expression with terms, with like terms, such as 6g plus 5g. Okay, so we're looking for common factors, and keep in mind that g is actually a number. We just don't know which number it is yet. So to avoid any problems with that when we're using the distributive property, because they both share g in common, g can actually be taken outside the parentheses with the distributive property. We're working with 6th grade numbers right now, and so in a minute I'm going to show you a little more complicated example where there are some numbers and letters that come out. But if I was going to explain how to simplify 6g plus 5g, first thing I would check for is numbers. So 6 would have factors of 1, 6, 2, and 3. 5 would have factors of 1 and 5. The greatest common factor is 1, so it's not really necessary to take a 1 outside the parentheses. Had I put a 1 here, that would have been nonsense. We wouldn't really write the 1 there. We know that 1 is not necessary to write in front of a variable, so that's why I didn't do that. Again, same thing. 1 is the greatest common factor. It's not necessary to take that and write it in front of the parentheses. G is a number too, and they do both share G, and it is connected with multiplication. So G is actually going to be the common factor that I'm taking outside the parentheses. G times 6 would be 6G, because remember, when we squish a number next to a letter, that means multiplication. So G times 6 would be 6G. Sometimes when students are just learning, they want to write G6. The rule of thumb for mathematics, we always write the number first to indicate how many G's we have. So if G times 6, 6 times G, we would call it 6G. And plus 5. All right, now that I've confused you, let's see what the book says. It says factor out the common factor G and simplify. So yeah, okay, we can do that. We've taken G out. We have 6 plus 5 inside. Those are now both constants, and I can add constants with other constants. G times 11, or 11G is how we would write that appropriately, because we have 11 G's for sure. Okay. Let's take a look here. It says a school cafeteria has 30 boxes of Wheaties square. You know, before we do this, real quick, if I had one like, say, 4x plus 6x, I need to check for both numbers and letters. 4 has factors of 1, 4, and 2. It's actually a perfect square number, so it has an odd number of factors. 6, 1, 6, 2, 3. Now, if 1 was the greatest common factor, we wouldn't really need to take it outside the parentheses, but in this case, 2 is the greatest common factor, so I do need to take a 2 outside the parentheses. I also see that these have an x in common, and that actually represents a number, so that also is a factor that can come outside. 2x times 2 would be 4x, and 2x times 3 would be 6x. So that's how we would factor or use the distributive property to write that sum as a product. You see, it's a little different now. Okay, now let's go ahead and look at this. It says a school cafeteria has 30 boxes of Wheaties Square cereal and 20 boxes of Mighty O's cereal. Each box has the same number of ounces of cereal. Write an expression to represent the total ounces of cereal, then simplify it to create an equivalent expression. So it sounds to me like they again want us to keep our like terms separate. So we have 30 boxes of Wheaties Squares and 20 boxes of Mighty O's, but they have the same number of ounces. And that phrase allows us to use the same variable for both. So I could draw 30 boxes, and it'd take me forever. But really, I know that if I have 30 boxes altogether, I would have 30x, and that would represent the number of Wheaties Square cereal, the number of ounces of Wheaties Square cereal. I would also have x represents the number of unknown ounces. We know they're the same number of ounces, but we don't know how many ounces are in each one. Plus 20x for the Mighty O's. There are 20 boxes of that with the same number of ounces in each box, but we don't know how many ounces that is. So I see 30x's and 20x's. I immediately know, oh, that's 50x's. However, in the Ready Math series is super important. Yeah, you probably can do that in your head. 30 plus 20 is 50, 50x. So I know my eventual answer is going to be 50x, but that's not really necessarily what we're working on today. We're working on using the distributive property. So when I think about 20 and 30, let's do 30 and 20, and I find the greatest common factor. I'm going to write out my list of factors if that's necessary. You may already know the greatest common factor. I'm going to squeeze a 5 and a 6 in there as well, and 20. But if it takes drawing the list out, that's fine too. It'll just take you a little bit longer. So when I look through this list for greatest common factors, I see they both share a 10, they both share a 5, a 2, and a 1. But the greatest of all would be the 10 for sure. So I know that I need to take a 10 outside the parentheses, and I also see that they share a common factor of whatever x is, 10x. 10x times 3 would be 30x, and 10x times 2 would be 20x. So really I have 10x times 5, or 5 10x's would make 50x. So yes, we have 30 here and 20 here, that makes 50 altogether, but using the distributive property, we can also see